Okay, welcome to everything you want to know about gas laws, but we're afraid to ask. We're going to run through the simulation and get some help for you on this project. What I did was I gave you the answers up here to the rearranging the equations algebraically. This pre-lab here was supposed to give us a way to get used to manipulating the equations. If you still don't know how to manipulate the equations, we've got that other sheet that you guys can refer to in section 2. So we have this handout here. I did make one slight boo-boo on this. This was an indirect relationship for Boyle's law, and it was a direct relationship for Charles and a direct relationship for Lussac. With that said, whatever I do to pressure, the opposite is going to occur in volume. Okay. For a direct relationship, whatever I do to volume, the same thing is going to happen to the temperature. So if I raise my volume, I raise my temperature. If I have Gay-Lussac's law and I raise my pressure, that means my temperature has to go up too. Those are direct relationships. Okay, let's look at section 3. All right, let's look at this one more time. If you don't remember what volume of a gas is, it is the space that the gas occupies. We measure that in liters. And the pressure is the force the gas exerts over an area or the space that it occupies, like the container. So that's measured in atmospheres or ATM. Temperature is not just heat, but a deeper meaning of temperature would say that it's the kinetic energy of a gas. It's how many collisions are happening and how quickly the gas particles are moving. Those are measured in kelvins or capital K. If you don't remember, Kelvin is equal to degrees Celsius plus 273. All right, let me get a different color here. Boop. Let's do blue. And our first sim was Boyle's law. Boyle's law is the relationship between pressure and volume. It's a direct relationship. So we started to play with the simulation, and this is what we came up with. We reduced our volume to 1.70. So my initial volume was 3 liters. My initial pressure was 1 atmospheres. I know my new volume is 1.70 liters. I just don't know what my new pressure becomes. I do know from observations that when I changed my volume, I actually got more collisions and the particles got faster. So taking a quick look at my table for equations, under Boyle's law, if I need to find P2, I can simply say it's P1 times V1 over V2. Now I substitute those values in. My initial pressure was 1, my initial volume was 3, my final volume is 1.7. This rounds to 1.76 atmospheres. My liters cancel. Okay, I think you guys were pretty good with that. We did another experiment where we changed the pressure. We lowered the pressure to 0.7. All right, that slowed down our gas particles. That gave us less collisions. So my initial pressure was 1 ATM. Initial volume was 3 liters. My new pressure is 0.700 atmospheres. I just don't know my second volume or my final volume. So from the table, I would look up for volume 2 under Boyle's law, and I'm going to find P1 V1 over P2 is my equation. Now I just have to substitute in my known values. My initial pressure is 1 ATM. My initial volume is 3 liters. And my final pressure is 0.7008 atmospheres. That rounds to about 4.29 liters, and atmospheres clearly cancel. All right, all right, all right. Let's look at the fourth question. On the fourth question, we're supposed to do multiple changes in pressure. So initially, you start out with 1 atmosphere of pressure. Your volume is 3.00 liters at that point, and that is taken right from the simulation. Okay, now I need to change my pressure to 1.50 atmospheres, and you'll see that your volume changes to 2.00 liters. All right, so you can actually do this under Boyle's law by changing your pressure. You can raise it, lower it, using the arrows. So if I need 1.5 atmospheres, I'll click calculate and it'll tell me the answer was 2 liters. If I need to go to 2 atmospheres, I raised it up and it calculated it for me at 1.5. If I need to go to 2.5 liters, I can go to find 1.2, okay? And so on and so forth. So at 2 atmospheres, my volume is 1.5 liters. At 2.5 atmospheres, I'm at 1.2 liters. And at almost 3 atmospheres, 2.90, my volume is 1.03 liters. What are the trends happening? Okay, based on the data, if I increase pressure, then I'm decreasing volume. So the opposite is occurring within the variables. If I increase pressure, then volume goes down. So is that a direct or an indirect relationship? Now, in a direct relationship, remember, there's 2 variables, and if you change one, you get the same change in the other variable. But in an indirect, where you change one variable and you get the opposite change. All right, so considering what we just learned from our manipulation, what kind of relationship is Boyle's law? Boyle's law is going to be an indirect relationship. In part F, when we're asked to make a prediction, if the pressure of the gas goes up because you squeezed it, you're reducing the volume, that shows an indirect relationship. So I said the pressure increases. So when you squeeze the bottle, volume goes down, pressure goes up. It's an indirect relationship. Okay, quickly moving on to Charles' law. Paper over. You have to select the Charles' law tab, and then we're testing different variables with Charles' law. Okay, we're no longer testing pressure and volume. We're testing temperature and volume. Okay, Charles. So pressure, volume, and temperature are 3 variables. What doesn't get affected? Pressure doesn't get affected, only volume and temp. Using the temp controls, what happens to the particles? What is happening when I increase the temperature? If I increase the temperature, let's do an observation. I'm going to blast it. They have more room to move around. But they're also getting faster themselves, and they're having more collisions. So I would say in 2A that they get faster, they have more room, and they also end up getting more collisions. That's when I increase the temperature. They get a little faster. There was definitely more room, and you get more collisions. So that leads us to explore this relationship then between volume and temperature, right? So let's say we increase it to 443 Kelvin. Use Charles' law equation and find the new volume. So V2 from my chart of equations under Charles' law, V2 is T2 times V1 divided by T1. All right. Substitute in 438 Kelvin times 3.00 liters all over 298 Kelvin. And my answer is rounded to 4.41 liters. Based on that information that we just calculated, do you think Charles' law is direct or indirect? Well, it would seem that if my temp goes up, then my volume goes up too. So I'm going to say that's a direct relationship. Right? If my temperature went up, then my volume also went up. And you can write complete sentences. You don't have to do it shorthand like me. Okay, moving on to the other example here. I noticed that it was slower. There were less collisions when we changed our volume. But one of the problems with this one was getting it exactly at 1.86. Some of us were running into a snag, so you could have rounded it to 1.9. So let me hit reset and change my volume. As I change my volume to 1.86, I can't get 1.86. I can get 1.8, I can get 1.9. We'll just round it at 1.9, and we'll leave it at that. So I'm asked to find out what is the new temp after I've changed my volume. Okay, so the temperature started out, let's say we want to find T2. Well, T2 is V2 times T1 over V1. And when it's all said and done and I substitute and I solve and I round for sig figs, it's 189 Kelvin. Okay? So what is that in Celsius? The next question asks. Well, I need to say 189 Kelvin minus 273 is equal to negative 85 degrees Celsius. And moving right along on the fourth one, we were asked to plot these data points when we increase the temperature 3 additional times. Okay, so you had about 5 sets of data. And as they went along, every time your temperature went to the right, that's an increase. And every time your volume goes up, that's an increase. So with volume increasing, you also get temperature increasing. So if my volume goes up, then my temperature goes up. With that said, what would happen if we double the... Let me make sure I'm reading this right. Yeah, let's say if we double the temperature, the volume doubles. Because whatever I increase one by, I'm going to increase the other by. And vice versa. If I decreased it, I'd have to decrease the other one. So if I doubled the temp, I double the volume. Let's move on to a similar law. Gay-Lussac's law is going to be our last one. On Gay-Lussac's law, it's most similar to Charles' law. This equation looks very similar to Charles' law. But there's one variable we're not testing. So we're only testing pressure. We're testing temperature. What do we leave out? Volume. We leave out volume. So if I am only testing pressure and temperature, what would happen if I increase the pressure? I squeeze a bottle, per se. All right. If I increase the pressure, then I increase the temperature. So that is another example of an indirect relation. Of a direct relationship. Let's get some data points plotted out on the sim. So you're going to need to go here and go to Gay-Lussac's law, and you plot out your data points. It says pressure 1 atm, volume 3 liters, temperature 298. Well, let's go ahead and change my pressure to 1.5. Sorry, that should have went up. 1.5. And let's see what happens to my temperature. Boom, 447. Let's go ahead and add another set of data by clicking this add data above the graph. And I'm going to increase the pressure to 2 atmospheres, hit calculate, and add another set of data. I'm going to increase the pressure to 2.5 and calculate, add one more data point, and I'm getting a trend. I'm collecting the data here, going to 2.9 atm, and I get 864. As the pressure goes up, what do we see happening to the temperature? Good, you're correct. It goes up. So the temperature increases. So that is a direct relationship. Okay, moving very quickly to question number 4. One of the observations is that it got slower, you had less collisions. And what you're going to have to do for this one is, if you're looking for P2, use your table with all the equations. Substitute and solve. You should get about 0.530 for that one. In this one, if we manipulated the temperature by 1/2 its original temp, then that means that the pressure decreases by 1/2, because that's a direct relationship. All right, the last part, let's take a closer look at. These are mixed word problems. First of all, this one here deals with volume and temperature. Volume and temperature is Charles' law. The second one here deals with temperature and pressure. Temperature and pressure is Gay-Lussac's law. And the last one is only volume and pressure, so that's Boyle's law. I have to be strategic with this. I have to give a close look at what the problem gives me. Let me use a highlighter. If I have to calculate the temperature of a gas when it's expanded to 5.25 liters, that tells me that it expanded to 5.2 liters. That tells me that's the final volume. The gas originally, that tells me it's the initial volume, was 3.54 liters of space, okay, again, relating to volume, at 282 Kelvin. That's a temperature. So first, it was 3.45 liters. Then it became 5.25 liters. Originally, it was 282 Kelvin, but final temperature we don't know. So I looked on my table of equations and I chose to find final temp, T2. And I'm substituting in 5.25 liters times 282 Kelvin divided by 3.45 liters. That's about 429 Kelvin. And I'm done with that one. Okay, so there it is, all on one view. Okay, in the second one, a temperature is increased from 125 to 182. Note these are in Celsius. So I already know I'm going to have to convert. Inside a rigid container, so the volume isn't going to change, but the pressure originally was 1.22 atm. What is the new pressure? What will the pressure be after the temperature change? So 125 Celsius plus 273 gives me an initial temperature of 389 Kelvin. Temperature 2, 182 Celsius plus 273, gives me 455 Kelvin. Moving over, I've got my original pressure of 1.22 atmospheres. I don't know my final pressure. So I'm going to use this manipulated version of the equation. All right, so Lussac's law says that P2 is equal to P1 times T2 all over T1. Let me substitute in those values for you. 1.22 atmospheres times 455 Kelvin divided by 389 Kelvin. And you have to use Kelvin with the gas laws. You have to convert. The reason being, it won't work with Celsius. Celsius has negative numbers, Kelvin does not. So always use Kelvin when we're doing gas laws. Our approximate answer is 1.43 with 3 sig figs, and the unit is atmospheres. Okay, very last one. My initial volume, 3.24. Standard pressure is 1 atm, so that's my original pressure, P1. And we want to know what the volume will be. So we want to know V2 if I increase my pressure to 1.2 atmospheres. This deals with Boyle's law. Remember, P1 V1 equals P2 V2. Well, if you're solving for V2, you can say that P1 times V1 divided by P2. So let's substitute in and solve that. I'm going to say that's equal to 3.24 liters times 1 atmosphere of pressure divided by 1.20 atmospheres. And our sig figs require us to round. It's 2.7. Let me check my calculator. Oops. All right, 2 seconds and I'll do it on the calculator. Come on, TI. Oh, I got 2.7 exact. Okay. So for sig figs, I'm going to add a trailing 0 after this decimal so I can have 3 sig figs. That's the only thing I had to double check. And the answer again is in liters. So atmospheres cancel. All right, that's a wrap. I hope this helps. We'll see you next time.